In the last two videos, we looked at constant cross-sectional bars, but as you know, most materials don't have that simple geometry. For example, if you take a muscle, then it might be bulged in the middle and it might taper off at the ends, and it might not be made of the same material. So it will be muscle fibers in the middle, and there could be some tendons at the end that attach to the bones here and here. So some muscles might even have multiple branches. So for example, in the bicep muscles, we know that it has two orisons. So it would have two tendons that attach to different points. So how would we model this kind of a system where there are different materials, different cross sections, um, and different number of attachment points? One way to do it would be to divide it into different parts. So let's say we divide this one into this. So this part has an approximately constant cross-sectional area, and we divide it into this, divide it into this. So we divide this part and this part separately, and then these parts. So you can see there are one, two. Let's number them. Let's call this 1, 2, 3, 4, 5, 6, and 7. So you have 7 different components, and if you wanted to make a spring system out of these 7 components, then it might look something like this. There's one spring, 1. We could call it K1 for the spring constant, or the K is understood, so we could leave it out. 2 springs, and so 1, 2, and 3 are in series, and then it branches into 4 and 5 from 3, 4, and 5, and then this 4 and 5 have different attachment points through different tendons. So 7, 4, it attaching to 7, and 5, it attaching to 6. So let's say we know the material properties of the tendon, like E tendon, and we know the material properties of a muscle fiber, so let's call it E muscle. Then you can calculate the spring constant equivalent to this if you know the lengths L1, L2, the initial lengths L1, L2, L3, and the initial diameters or the cross-sectional areas. So if you assume that it's circular, then from the diameter you can get a cross-sectional area, and we know from previous videos that the spring constant, so let's say K1, so because K1 is a tendon, we'd use the elastic modulus of the tendon that we can take from tables of known tendons of similar muscles from similar species, and it will be you multiply it by the area of that section, and divide it by the length, the initial length of that section. So call it L10. So similarly, K, so the nth K will be equal to either E muscle or E tendon, depending on whether it's a muscle section or a tendon section. So E2 will be EM, and E7, 6, and 1 will be ET, and the area of the corresponding section So let's say AN and the length, initial length of that section. So let's say we found out the spring constants of the individual sections. So now it would be difficult to calculate the uh, lengths and displacements and the forces of each of the sections separately. So to simplify this network, we could use a single spring here that covers all 1, 2, and 3. Let's call it K1, 2, 3. And then the 4 and 7 can be combined to get K4, 7. And 5 and 6 can be combined to get K5, 6. So what would K1, 2, 3 be? It's not very difficult to prove that K1, 2, 3 will be will add like resistors in parallel. So it would be 1 by K1 plus 1 by K2 plus 1 by K3. So I'll refer to other websites or other videos to prove that this is the case. But basically, what I want to show here is that you can simplify this network of different materials into an effective spring constant that is like a composite, and yet still be able to model the behavior of this whole spring network. So what you might have noticed is that none of these contain any masses, and we're only talking about springs, and it doesn't have any viscosity or damping coefficients, and it doesn't have any masses. While we know that if you take a muscle, then it probably weighs something that is not entirely equal to 0. So let's say we have a muscle like this, and it has tendons at the ends. So the mass of the muscle here, where does this go? Does it go, so let's say this has a certain mass M. So where would you put the mass of the section? So you have it modeled like a spring with a spring constant K. So would the mass go over here or over here, or maybe on one side but not the other? Or maybe you can divide the mass into two and distribute it at the two ends. So you could go with either way, or you could chop up the spring into two and put the mass in the middle. So why would you want to include the mass? If you are doing a dynamic simulation which has to look very realistic, for example, if you want to simulate surgery, or you want to do a computer animation for visual effects, then you would want to simulate the shape of this quite accurately, and you might want to divide it into many small segments and calculate the K effective for each of these small segments and distribute the mass accordingly according to the densities of the material. So if you know the length of the segment, the cross-sectional area, and the elastic modulus and density, then you can, from the elastic modulus, you can get the K, and from the density, you can get the mass of that segment, and you could model this as a mass spring system with many different springs. So once you have many, then it becomes the diagram doesn't look very clean if you put in the spring symbols. So you just link them and form a network of mass and springs. So most often though, you are not even interested in the shape of the muscle itself and only the force it applies at the ends. And you can many times just ignore the mass. So you would model this muscle very simply with a few springs and possibly a contractile element. And that's what the Hill model is, or any Hill-like muscle model just has few springs, for example, in series to a contractile element. So the contractile element is often written CE, and you'd have the other spring in parallel, and this whole network models this whole thing. And even though it might have two attachment points, you could combine them and assume that it attaches to a similar point, and combine them into a single system where you have the series element that is series with the contractile element and the parallel element that is in parallel with the contractile element. Now this is able to give you the force it applies at the ends, but it might not be able to give you what shape the muscle takes. Or you could use other simplifications to assume that uh, you know if you know the thickness over here, you could smooth out the other thicknesses and say this will be a smooth function, and from there calculate the shape.